Hi, my name is Leo. Today I'm going to talk about gamma ray spectroscopy, what gamma spectroscopy is and how it works. Gamma ray spectroscopy is the quantitative study of the energy spectra of gamma ray sources. Radionuclides commonly emit gamma rays in the energy range from a few kiloelectronvolts to usually 3 megaelectronvolts, or some of them to 10 megaelectronvolts. Every radionuclide has its specific combination of energy levels. So we could say that gamma spectrum represents radionuclide fingerprint. Given that fingerprint, it can be determined which isotope we have in measured radioactive sample. So let's take a few examples of radioisotopes. The first one is Cobalt-60 with its two peaks. The first one on 1173 and the other on 1332 kiloelectronvolts, and we can see that both of them are Cobalt-60 peaks, meaning that Cobalt-60 directly decays in gamma. The other example is Cesium-137, which has its main energy photopeak on 662 kiloelectronvolts, which is Cesium-137 peak, meaning again that this isotope also decays in directly gamma decay. And the third example is Thorium-232 radioisotope. It has its three peaks. The first one on 238 kiloelectronvolts of lead-212, then the other on 338 kiloelectronvolts of actinium-228, and the third on 583 kiloelectronvolts peak of thallium-208. So we can see that thorium does not decay directly gamma, but its daughter elements in its decay chain do. There are more different spectrometers. The most important difference between spectrometer systems is in two factors. The first factor is resolution. Better resolution gives more precise measurement result. The other one is efficiency, which represents how many gamma rays is captured by a detector, and therefore higher efficiency means getting faster result. The biggest hardware difference is in detector and in electronic components of a system. The best example is spectrometer with a detector, which contains a semiconducting diode such as a high purity germanium diode that has a relatively low efficiency but great resolution. This detector is very expensive due to high quality parts and maintenance, which requires liquid nitrogen for cooling the semiconducting diode. Another example is a spectrometer I'm going to show you. The main parts of detector are scintillation crystal and photomultiplier tube. Detectors with scintillation crystal are very efficient but have relatively low resolution, which means that due to low resolution they will not be able to detect peaks of energy which are too close to each other. Despite this, with this spectrometer, most of important radionuclides can be identified. These are the three main parts of gamma spectroscopy setup. The first and the most important is detector. Detector consists of scintillation crystal and photomultiplier tube. The crystal we have here is cesium iodide doped with sodium crystal. Here we have the main parts of the detector. This is the crystal, but this one is sodium iodide doped with thallium crystal. And since it is very hygroscopic, it is enclosed in this container with glass window. Here we have plastic scintillator and photomultiplier tube. In this window we can see the photocathode, and here are dinodes. Now I'm going to explain how the detector works. It consists of two parts, scintillator on the left and photomultiplier tube on the right hand side. So first a gamma ray, which is a high energy photon, strikes the scintillator, leaving an ionization track there. Also a scintillation flash appears, which are actually low energy photons, which then strike photocathode. This photocathode then emits electron or more electrons beam, and this electrons beam is then focused in focusing electrode to the first dynode. On the first dynode, number of electrons is multiplied, and this electron beam further goes to the second dynode where it is again multiplied. So on each subsequent dynode we have multiplication of the electrons number, and when the electrons beam come to the last dynode, which is anode, we have the impulse. So the higher energy has a gamma ray in the beginning, we would have more electrons in the end and stronger impulse. The second most important part is this box, which has high voltage power supply, preamplifier, amplifier, and analog to digital converter. And the final part is this computer software, which is multi-channel analyzer, and this one we have here is Thorium MCA. Now I'm going to show you how these impulses are distributed in channels, and you're also going to see that in the picture in top left corner. At the moment on this oscilloscope you can see background radiation. And now I'm going to put this radioactive source close to the detector and push this button at some moment to stop data acquisition and get a suitable example for this presentation. For example, this one. Here's the cursor. I'm going to move and come and use to measure height of an impulse. And here is delta Y value, which tells us in millivolts or volts how much is an impulse high above from the baseline. The first one is at 112 millivolts, then 416 millivolts, 168 millivolts, 304 millivolts, 344 millivolts, and 528 millivolts. And that's enough for this presentation. Here is an example of a spectrum graph we've got using 6 impulses from measurements on oscilloscope. We've divided the graph into 6 channels, each of which has interval of 150 millivolts. We can see there are impulses on the first 4 channels, and most of them, 3 of them exactly, are in the third channel from 300 to 450 millivolts. And if we would like to say which isotope it is about, we would compare this graph to graphs of other isotopes and say it is the isotope which has the peak in the third channel in this interval from 300 to 450 millivolts. Here you can see the entire gamma spectroscopy setup, and here we also have the sample. So it's actually the camera which has here in its lens the radioactive sample we are going to identify. First, to start new measure and turn on the sound, and what you can hear now are impulses of background radiation. Now I will bring this camera sample closer to the detector and you'll hear more impulses. start new measure to identify the sample. And now we have to wait some time until we get more clear peaks at the graph. We can already see some graphs. This peaks, this first one at 238 kiloelectron volts, then this second one at about 338, and this one at about 583 kiloelectron volts. So according to these peaks, we can say and conclude that the sample we have is thorium 232. Now only to prove this, select sample, and we can see these three lines which indicate these three peaks. So the first one we've already identified is peak of lead 212. The second peak is peak of actinium 228, and the third peak is peak of thallium 208. What we can notice that here is no peak of thorium 232 itself, which means that thorium 232 does not decay in gamma directly. It decays in some other type. In this case it is pure alpha, but its daughter elements, so elements which are in its decay chain, have gamma decay. And these are these three elements. So thanks to these three peaks and to this gamma spectrum, we can conclude that the sample we have here is thorium 232. In this video you've learned all about gamma spectroscopy. Hope you've enjoyed. Thanks for watching and stay with us.